set to record. And just as a reminder, all of the recordings are posted on our class channel. Okay, so let's do some review. So we're dealing with writing out net ionic equations from phrases. So we're going from a word expression into a chemical equation. So solutions of barium chloride and copper 2 sulfate are mixed, yielding barium sulfate and copper 2 chloride. So first and foremost, we need to write the formulas. So would someone like to volunteer a formula for barium chloride? Barium chloride. And don't be shy to type in the chat. Yep, BaCl2. So we have barium 2 plus, chloride Cl minus. We cross our charges, and that gives us BaCl2. Okay. Copper 2 sulfate. So we have copper 2 plus and sulfate, which is SO4 2 minus. We cross our charges, and that gives us CuSO4. Okay, would someone like to provide a formula for barium sulfate? Barium sulfate. I think we've handled that compound before and seen that compound before in the lab. And don't be shy to type in the chat. Yep, BaSO4. Barium sulfate. Okay, and then copper 2 chloride. So just to show the work for barium sulfate, barium 2 plus, SO4 2 minus, we cross our charges, gives us a 1-to-1 ratio. Copper chloride, we have Cu2 plus, Cl minus, we cross our charges, that gives us CuCl2. Okay, now we have to check, and it looks like this equation is balanced, so that's good. Now we need our equation with the proper state symbols. Notice how I left the state symbols blank. My question to all of you is, what would the state symbol be for barium chloride? And remember, barium chloride is a chloride salt. So aqueous, yep. Chloride salts are overwhelmingly soluble. What about copper sulfate? Copper sulfate. So sulfate salts, we have to think of the exceptions. Is copper one of the exceptions? Is copper one of the insoluble sulfate salts, or is copper sulfate soluble? What symbol do we put for copper sulfate? So in terms of our sulfate list, sulfates are soluble for the most part, except for calcium, barium, lead, mercury, and a few others in the table. Remember the table on page 3. Okay, barium sulfate. Just as a reminder, and this is a nice way I like to remember barium solubility. Barium metal is actually quite toxic. Barium 2 plus is a toxic metal ion, but we can easily drink and consume barium sulfate. Would you expect barium sulfate to be soluble or insoluble? Soluble or insoluble? Is barium the exception for sulfate solubility? It's insoluble, exactly right. So we put a solid. Copper chloride, being your typical chloride, is soluble. Perfect. Now we're ready to write out an ionic equation. So what we're going to do, quite simply, is we're going to dissociate all of our soluble ionic compounds. So barium chloride gets broken up into barium 2 plus and 2Cl minus. So if you've already done the work and have generated the formulas, you've actually given yourself a wonderful guideline for writing out the ions after dissociation. You know, it's always good to maximize efficiency. Copper sulfate breaks down into copper 2+, as I've already written, and sulfate, which I've already written. Do we break up barium sulfate? Do we break up barium sulfate? No, we keep it together. It's an insoluble ionic compound, and we only dissociate our soluble ionic compounds, strong acids, and strong bases. Copper chloride breaks down into copper 2+ and 2Cl-. Okay, now what we're going to do is we're going to cancel our spectator ions. Are there any other spectator ions in this equation? I canceled one of them just as reference. Are there any other spectator ions? Copper 2+, that's exactly right. Okay, so that in turn gives us the following net ionic equation. This type of reaction is known as a precipitation reaction because it generates an insoluble precipitate, an insoluble solid. Okay, so we're still getting used to this idea of net ionic equations. So now that I've shown you another example, let's have you practice. So given that we have solutions of potassium iodide and lead 2 nitrate, and we mix them to yield potassium nitrate and lead 2 iodide, I'd like everyone to take a moment and try to process each of these names into a chemical formula. So you're welcome to message me the name, the formulas for each of these names. Then we'll come together as a group, we'll bring together all of our formulas to generate a cogent chemical equation. We'll then try to balance the equation and assign physical states. So let's take about 2 to 3 minutes and write some formulas for these names. And don't be shy to message me in the chat with your proposed formulas for each of these names. And we'll discuss in about a minute and a half. Okay, so let's discuss as a group. Let's discuss as a group. Would someone like to provide a formula for potassium iodide? So what would the formula be for potassium iodide? Yep, Ki is exactly right. Would someone like to provide a formula for lead 2 nitrate? So So again, you have to be familiar with your nomenclature to begin to approach these problems. So lead 2 nitrate. Yep, PbNO3, that's exactly right. And we have 2 nitrates because to accommodate our lead 2 plus charge, if nitrate has a -1 charge, when we cross our charges, we get PbNO3 too. Okay, can I get some responses in the chat? What is the formula for potassium nitrate? What would the formula be for potassium nitrate? KNO3, yeah. Okay, and what would the formula be for lead 2 iodide? Lead 2 iodide. Yep. PbI2, because we're crossing lead 2 plus, iodine minus, we cross our charges, we get PbI2. Okay, let's rewrite our equation. And now let's take a look and see whether we need to balance the equation. Okay, so is this equation balanced as currently written? Is this equation balanced as currently written? No. So if we look, we see we have 2 iodines on the right, and we only have 1 iodine on the left. So what times 1 would give us 2 iodines? 2. Yep. We also see we have 1 nitrate on the right, and we have 2 nitrates on the left. So what times 1 would give us 2? What coefficient should we guess? And let's try to get some more responses in the chat. 2 is exactly right. Perfect. So now we balance the equation. That's all fine and well. Let's now rewrite our balanced equation. And let's assign state symbols. So potassium iodide, soluble or insoluble? It's a potassium salt. Is that soluble or insoluble? Soluble, exactly right. Okay, lead nitrate, soluble or insoluble? Nitrate salt, so those typically soluble or insoluble? Soluble, exactly right. So it gets an aqueous symbol. Potassium nitrate, KNO3, soluble or insoluble? It's a potassium salt and a nitrate salt. I like to joke it's doubly soluble in a way. So this one also gets an aqueous symbol. Lead 2 iodide, so PbI2, soluble or insoluble? So halide salts are soluble for the most part, except for what major exceptions? I see students commenting that's a solid. That's right. Lead, mercury, and silver are exceptions to our solubility rules. Okay, now let's write an ionic equation. So what we're going to do is we're going to take each of our soluble ionic species, strong acids and strong bases, and we're going to dissociate them. So we dissociate potassium iodide, remembering that our chemical reaction coefficient applies to each ion in our chemical formula. Lead nitrate breaks down into lead 2 plus aqueous plus 2 NO3 minus. So notice how each of the methods that we've used to build our equation are also used to build our net ionic equation. So there's a reason why I have you do things in a certain order. It makes things easier when you're writing your net ionic equation. Okay, and do we dissociate this lead to iodide? Do we dissociate lead to iodide? Do we dissociate this species? No, exactly right. Okay, now all we have to do is identify our spectators. So what are examples of spectator ions? What are the spectator ions? Nitrate, that's exactly right. What else? Potassium, that's exactly right. Perfect. So we end up with the following net ionic equation. Pb2 plus aqueous plus 2I minus aqueous leads to PbI2 solid. And again, this is a precipitation reaction. And just as a rule of thumb, for most precipitation reactions, the net ionic equation will be the combination of our two ions to generate an insoluble ionic compound. Wonderful. Now, on this note, I've been showing you a bunch of precipitation reactions. Let's talk about those precipitation reactions now. So a precipitation reaction, quite simply, is mixing solutions of soluble ionic compounds to give an insoluble ionic compound that we call a precipitate. So in this case, the barium sulfate, which is our insoluble ionic compound product, is our precipitate. So your goal, or your rule to predict precipitation reactions, so suppose I just gave you the reactants, how would you go about predicting a precipitation reaction? Well, first things first, you write out your reactants. Those will be given to you. You're going to dissociate all soluble ionic compounds, strong acids and strong bases. So you're going to break them up into their component ions. And now you're going to play a bit of a mix and matching game where you're going to pair each cation with each anion, and you're going to pair each anion with each cation. And then we're going to make a table. We're going to write a list of all possible ionic compounds. And what we're going to look for is we're then going to go to our solubility table, and we're going to say, are any of these ionic compounds insoluble? The insoluble ionic compound that can be formed from the ions in solution is the precipitate. Okay, so let's showcase this thought process. So we have each of our ionic compounds. I even give you the state symbols since I'm being generous for this problem. We're now going to dissociate each of our soluble species into their component ions. Don't worry about the stoichiometry for now. We're not aiming for a balanced equation here. Okay, so now we're going to play a bit of a mix and match game. So we can obviously pair silver with nitrate and potassium with iodide. That's option one. So let's write those formulas here. So we have silver nitrate and potassium iodide. So that's option one. In option two, and if you're predicting precipitation reactions, we're going to swap our anions. So we're going to swap silver and nitrate. And so for option two, we have silver plus iodide anion and potassium plus nitrate. Note, I haven't actually changed anything about the chemical equation. I'm just drawing it in a slightly different way. Okay, so we have as our options silver iodide and potassium nitrate. And notice how all of these formulas are charge balanced. That's really important. You're not just swapping the anions, but then you're going through and you're writing out the chemical equation for each product that could form by pairing those ions. Okay, so now we have this list, and now we're going to go to our table, and you're going to tell me each of the state symbols. And we're looking under our two options, 1 and 2, do we see an insoluble precipitate? So let's start with silver nitrate. Is silver nitrate soluble or insoluble? And this one should not take very long because the answer is actually right in front of us on the page. Soluble, exactly right. Potassium iodide, soluble or insoluble? Potassium iodide, soluble or insoluble? Soluble, exactly right. I mean, by definition, if you start with two solutions, those species are going to be soluble if they're homogeneous. Okay, silver iodide. What state symbol do we give for silver iodide? Solid. Yep, it's insoluble. And potassium nitrate is aqueous. Okay, so with this information in mind, we're going to look at option number 2. So we're going to write out, we have silver plus aqueous plus NO3 minus aqueous plus I minus aqueous plus potassium plus aqueous. And in this case, our insoluble product is going to be silver iodide solid. And as a byproduct, we're going to make potassium plus aqueous and NO3 minus aqueous. Okay. So I'm just going to put a box around my precipitate. Now, as a question for all of you, what are our spectator ions in this case? What ions are identical on both sides of our chemical equation? Nitrate, yep, so we can cross that out. What else? Potassium, perfect. So now all we have to do is write out our final net ionic equation, which for a precipitation reaction will overwhelmingly be our component ions combining and reacting to yield our insoluble precipitate. There we go. Perfect. So let's keep going now. Now, a really critical point, and this may seem somewhat redundant to say, a precipitate must form for a reaction to occur. If it doesn't, no reaction has occurred, or no precipitation reaction at least. If all of the ions, elements, and compounds in the net ionic equation cancel, no reaction has occurred. So let's take a moment and let's look at the following example. So I'm immediately going to dissociate each of our ionic compounds into their component ions. So we have 2 sodium plus, we have 1 carbonate, we have 2 potassium plus, and 1 sulfate. Okay. Now we're going to make a list of ionic compounds, and we're going to use our old trick. We're going to swap our anions. So we have 2 sodium plus aqueous plus SO4 2 minus aqueous plus 2 potassium plus aqueous plus CO3 2 minus aqueous. Now, I'm just writing it this way so it's easier for me to write the formulas. So would someone like to tell me what 2 possible ionic compounds can we form from these ions? What 2 possible ionic compounds can we form from these ions from the way that I've written it in blue? And just make sure you're accounting for charge balance. So I saw someone mention sodium sulfate. That's correct, but we have to keep in mind our charges. We have sodium plus and SO4 2 minus. So when we cross our charges, we would get Na2SO4. Okay. So this is one option. And as a byproduct, we'd get potassium carbonate. Okay. Our other option is just sodium carbonate and potassium sulfate. Okay, let's check our state symbols. We know that for sodium carbonate, it's aqueous. Potassium sulfate is aqueous. Let's check the state symbols of sodium sulfate. Is sodium sulfate soluble or insoluble? Is sodium sulfate soluble or insoluble? Soluble, exactly right. So it gets an aqueous symbol. Is potassium carbonate soluble or insoluble? Potassium salts, which such as sodium, salts such as sodium, lithium, and potassium are overwhelmingly soluble or insoluble. Soluble, yep. So this potassium carbonate gets the aqueous symbol. Okay, so as we can see, no matter how we pair our ions, fundamentally, we have our pool of ions, sodium plus aqueous plus SO4 2 minus aqueous plus 2 potassium plus aqueous plus CO3 2 minus aqueous. These ions in turn will lead to 2 sodium plus SO4 2 minus plus 2 potassium plus CO3 2 minus. Do we have entirely spectator ions? So let's list our spectator ions for this reaction in quotes. What are our spectator ions in this case? Sodium, yeah. What else? All of them, yep. So there's no actual reaction. So the net ionic equation is telling us we have no reaction. Perfect. So in this case, you can clearly see by dissecting this equation, we don't generate an insoluble precipitate, so there's no precipitation reaction. Perfect. So let's keep going now. And I'd like you to predict the products of the following reaction and write a balanced chemical equation, total ionic and net ionic equation for each reaction. So I just want you to remember that the following acids are not strong acids. So these, as a result, you shouldn't dissociate the following species. So let's take a moment and let's give our best attempt at writing a net ionic equation for the following first reaction. And then we'll come together as a group to discuss in about 4 to 5 minutes. And you're welcome to message me with your predicted products for this reaction, as well as your proposed balanced equation, total ionic, and net ionic equation. And I really do encourage you to send me your proposed responses so that way I can provide feedback. So we'll discuss in about 4 to 5 minutes. Any questions so far? Don't be shy to message me with questions or your proposed responses in chat. I want to make sure that everyone has enough practice on these net ionic equations, and predicting precipitation reactions. And we'll discuss in about 2 to 3 more minutes. I'm seeing a few students propose balanced equations. That's good so far. Perfect. So I see some proposed responses. So let's talk through this problem. So first and foremost, we're going to take each of our chemical species and we're going to dissociate our soluble ionic compounds, strong acids, and strong bases, okay? So we break down our zinc nitrate into zinc 2+ and 2 nitrate ions. Hydrosulfuric acid stays together. And now what we're going to do is we're going to try and we're going to pair each of our cations and each of our anions. So I'm going to swap the nitrate and sulfide. And that in turn gives us zinc 2+, aqueous, and S2-. So we aren't dissociating. We're just trying to predict and see, do we observe an insoluble precipitate? So we'd predict to observe as one of our potential options, zinc sulfide. And if we have 2H+ and 2 nitrate, we end up with 2 nitric acid. So since we observe generation of an insoluble precipitate, we do observe a precipitation reaction. So what we're now going to do is we're going to write out our equation. So we have zinc 2+ aqueous plus 2NO3- aqueous plus H2S aqueous. And then in terms of our products, whoops, I got a little ahead of myself there. This is zinc sulfide solid. So we generate zinc sulfide solid as well as nitric acid. And since nitric acid is a soluble strong acid, we're just going to dissociate nitric acid into 2H+ aqueous plus 2NO3-. aqueous. Okay, now that we have our predicted products, let's just rewrite our equation once again. So again, just to be 100% clear here, we swapped our cations and anions. We paired each of our cations and anions, and we looked to see, do we observe an insoluble ionic compound? And zinc sulfide, sulfite salts are a big red flag because those are clearly insoluble species. Now, taking a look at the following equation, are there any spectator ions in this equation? Are there any spectator ions in this equation? Are there any spectator ions? Nitrate, exactly right. So we can cross that out. And then for our net ionic equation, we have zinc 2 plus aqueous plus H2S. Aqueous leads to zinc sulfide solid plus 2H plus aqueous. Perfect. So there's our complete net ionic equation. So again, just to highlight the thought process, you dissociate all of your strong electrolytes. You then swap your cations or anions and draw out the proposed formulas of ionic compounds that you generate. If you see an insoluble species, that's going to be your precipitate. And then you write out the products from pairing your ions to generate the precipitate. Then you cancel out your spectator ions and you're left with your net ionic equation. Does that make sense to everyone? Does that make sense? Any questions on this example? Okay, let's keep moving on then. So let's tackle one more example. So I'd like you to predict the products of the following reaction and write a balanced chemical equation, total ionic, and a net ionic equation for each reaction. So let's take another 4 to 5 minutes and let's try and process the following chemical equation to get an equation for our products, our proposed total ionic equation, and a proposed net ionic equation. And you're more than welcome to message me with your proposed balanced equation as well as your proposed products for this reaction. So let's take about 4 to 5 minutes to work on that, and then we'll come together as a group to discuss. And you're more than welcome to message me with questions during this time. And just try, at the bare minimum for this problem, try to at least predict the reasonable precipitation product from this reaction. And Mariano, the idea is right, just make sure that your formulas are charge balanced. always make sure that when you cross your ions, you then rewrite the formula using our charge balance rules, just like we've done for other ionic compounds. And we'll discuss in about 2 to 3 minutes. But don't be shy to message me your responses for the proposed products from this precipitation reaction. So that way I can provide you some feedback, and so we can discuss your logic in solving the problem. Yep, I'm seeing a lot of reasonable responses so far for the predicted products. Let's try to get some net ionic equations, and then we're all set for this problem. Okay, so let's discuss this problem. So first and foremost, we're going to dissociate all of our strong electrolytes, which are soluble ionic compounds, strong acids and strong bases. So this in turn gives us lead 2+ aqueous, 2 acetate ions. Remember, the subscript tells you the number of each ion. Sodium iodide gets broken up. Whoops, I'm getting ahead of myself there. Sodium plus aqueous plus I minus aqueous. Okay, so now what we're going to do is we're going to swap our anions. So we have lead 2+ aqueous, I minus aqueous, and sodium plus aqueous and acetate. And we're not going to worry about the fact that there are 2 acetates for now. Okay, in terms of writing the formulas, we take each of our charges and cross our charges. So we get for our proposed products, lead iodide, and following a similar logic, we'd predict sodium acetate, which I'm going to write in the slightly more aesthetically reasonable way as follows. Okay, let's now assign state symbols. Is lead 2 iodide soluble or insoluble? Soluble or insoluble? Insoluble, so it gets a solid symbol. Exactly right. Sodium acetate, is it soluble or insoluble? Sodium salts, are they soluble or insoluble typically? Soluble, yep, so they get the aqueous symbol. So we have our precipitate of lead iodide. So now all we have to do is we have to take our equation Whoops, one moment. Let me reset OneNote. Okay, so now what we're going to do, now that we have our predicted products in place, now we're going to write our equation before dissociation, And the reason why we're doing this, the reason why we're writing our chemical equation before dissociation is we want to make sure that we've balanced all of our reaction coefficients properly. Okay. So first things first, let's write out each of our reactants. One moment, allow me one moment to reset OneNote. Give me 1 second to reload OneNote so that way the sharing doesn't have any lag associated with it. Okay, perfect. So we're going to write out our chemical equation before dissociation. State symbols and all. And we already have our predicted products from this method. Okay, and now what we're going to do, is we're going to balance this equation. So we have 2 acetates on the left. Well, we only have 1 acetate on the right. So what coefficient needs to go in front of sodium acetate? 2, exactly right. So as a consequence now, we have 2 sodium plus and 2 acetates. We also have 2 iodides on the right. So to balance out, if we have 1 iodide on the left, 1 times what would give us 2 iodide? 2. Okay, now that we've balanced our chemical equation, then and only then can we dissociate our ions. This is a common mistake I see students make. They forget to have a balanced equation before they dissociate, and they end up with ions not canceling properly. Okay, so now let's dissociate all of our soluble ionic compounds, strong acids and strong bases. And even when you're balancing the chemical equation, it gives you a nice ion inventory of all the species in solution. Do we dissociate our lead iodide? Do we dissociate our lead to iodide? Yes or no? Do we dissociate our lead to iodide? No, we don't. It's an insoluble precipitate. We do dissociate our sodium acetate to 2 sodium plus aqueous plus acetate. And we make 2 of them because our coefficient applies to both ions in our formula. Now let's cancel our spectator ions. So what are our spectator ions in this case? What are our spectator ions? Acetate, yep. What else? What else? Are there any other spectators? Any other species with the exact same charge and physical state? Sodium plus, yep, exactly right. So this gives us a net ionic equation of lead 2 plus aqueous plus 2I minus aqueous leads to lead 2 iodide solid. Perfect. There we go. Wonderful. Okay, so let's keep going with this process if there aren't any other questions. We'll leave this example for you to work on at home. There are 2 more examples for you to practice. And now we're going to review neutralization and acid-base reactions. So we've seen these in the previous chapter when we discussed acid-base chemistry, but I just want to provide you a refresher because we're going to use this information to start to predict the products of acid-base reactions. So the key feature of an acid-base reaction is they're characterized by the transfer of H plus or a proton from an acid to a base. So an acid is an H plus donor, while a base is an H plus acceptor. So the key feature when you look at the net ionic equation for an acid-base reaction is you'll clearly see the transfer of H plus from your acid to your base. We've seen this before in our discussion of acid-base chemistry. Let's look at a few common types of acid-base reactions, and this will really inform how we predict our products. So strong acids, so let's use an example, strong acids such as hydrochloric acid. Strong acids donate H plus to strong bases to form water and a salt. So for our strong base, let's use calcium hydroxide, a hydroxide equivalent. Okay, so our acid will donate a proton to our base, and in terms of predicting your salt, product, you're going to look at the conjugate base anion and your cation. So we have calcium 2 plus and Cl minus. We're going to cross our charges and we predict our salt to be calcium chloride. We'd also generate water as a byproduct. Now, at the heart of all acid-base reactions is the fundamental reaction between H plus and OH minus to generate water. So we need to have equal equivalents of H plus and OH minus. So looking at this equation as written, my question to all of you is, do we have a balanced equation? Do we have the same number of OH and H plus equivalents? No. If we have 2 OH equivalents, how many H plus equivalents do we need? So if we have 2 hydroxide equivalents, how many H plus equivalents do we need? 2. Notice how we balanced chloride as a result of this modification. And now if we have 2 H plus and 2 OH, how many water molecules will we make? How many water molecules will we make? 2. There we go. Perfect. So if we dissociate all of our strong acids, strong bases, and soluble ionic compounds, we get 2H plus aqueous plus 2Cl minus aqueous plus calcium 2 plus aqueous plus 2OH minus aqueous leads to calcium 2 plus aqueous plus 2Cl minus aqueous plus 2H2O. And as we notice, if we cancel our spectators, which are chloride and calcium, we are left with this same fundamental acid-base equation. So this is true for reactions of strong acids with strong bases. Wonderful. With weak acids and weak bases, you have to be a little bit more careful. So let's use our example of our strong acid once again, HCl aqueous. And for our weak base, we previously brought up the idea of ammonia, okay? So these species will react and will generate, in turn, a weak acid. So we're going to draw the transfer of a proton from our acid to our base. And we're going to now draw our conjugate acid product. So this would be NH4 plus aqueous, and as a byproduct, we make Cl minus aqueous. Now, looking at this equation, if we try to draw a net ionic equation, do we dissociate hydrochloric acid? Do we break hydrochloric acid into its component ions? Yes or no? Does hydrochloric acid dissociate? Yes, it dissociates into H plus, aqueous, and Cl minus, aqueous. Do we dissociate ammonia? Do we dissociate ammonia, which is a weak base? No, so we keep it together. Okay, ammonium, being a weak acid, is also kept intact. Chloride is already as dissociated as we can get it. Now, if we cancel our spectator ions, we notice fundamentally when we are reacting a strong acid and a weak base, our net ionic equation just looks like our weak base is picking up a proton, right? Fundamentally, acid-base reactions involve the transfer of a proton H+. Does this make sense to everyone so far? Does everyone notice how the net ionic equation helps reveal fundamentally what's going on in our chemical reaction? Okay, let's do another exercise. Let's do another exercise. So weak acids. So let's draw a weak acid such as acetic acid, for example. So weak acids donate H plus to strong bases. So let's do sodium hydroxide as an example. So weak acids donate a proton to strong bases to give a weak base as well as water. So our weak base in this case would be sodium acetate. So in terms of schematically what's going on, a proton's being transferred from our acid to our base. So let's now dissociate each of our strong acids, strong bases, and soluble ionic compounds. So do we dissociate acetate, considering it's a weak acid? Do we dissociate acetate, considering it's a weak acid? No, we do not. Exactly right. So we have acetate. Just one moment. Allow me one moment to reset OneNote. Sometimes it gets laggy with the recording. One moment. Let me just get OneNote back up online. and we'll continue our discussion. Okay, perfect. So we aren't going to dissociate acetate. We do dissociate our strong base, which is a soluble hydroxide salt. We do not dissociate water. And we dissociate our sodium acetate into acetate ion and sodium plus ion. Now, what are our spectator ions in this case? What ions do we cancel? What are our spectator ions in this case? What are our spectator ions in this case? Sodium, yep. Is acetate a spectator? Do we see acetate in the same physical state and charge on both sides? Not in this case. So only sodium is our spectator. So fundamentally, for reactions of a weak acid with a strong base, we have the transfer of a proton from our acid to our base. Weak acids and weak bases undergo reversible reactions. And in terms of net ionic equations, there's not much to do with these equations because there's no species to dissociate necessarily. We won't see these reactions a ton in this class. Okay, let's now talk about some common acid-base reactions and some common byproducts from acid-base reactions. So for neutralization and acid-base reactions, some acids and bases undergo decomposition reactions that generate gas. So gas-forming reactions, as their name implies, are reactions that generate gas. A decomposition reaction is the reaction of a compound to give one or more elements and or compounds. Okay? So the most common examples involve carbonic acid and sulfurous acid. Other gases of note are hydrogen sulfide and ammonia. So for example, if you take a solution of sodium sulfide and you treat it with 2 equivalents of hydrochloric acid, you will in turn make hydrogen sulfide gas. Other examples are if you have a solution of ammonium chloride aqueous and you treat it with sodium hydroxide, you can end up generating ammonia gas. Whoops, you need only 1 equivalent of sodium hydroxide for that. Okay, so in terms of decomposition reactions, one moment, let me get the zoom just right for this. Okay, so for decomposition reactions, carbonic acid decomposes to give carbon dioxide and water. So an example of this in a chemical reaction. So an example of this in a chemical reaction would be the classic baking soda and vinegar reaction, where if we have acetic acid, in this case reacting with calcium carbonate, we observe generation of carbon dioxide gas, water, and calcium acetate. So this carbon dioxide and water, it's coming from our carbonic acid that we generate. Another example of this is sulfurous acid, which is H2SO3, can decompose to yield water and sulfur dioxide. Do you notice how these reactions are relatively analogous in terms of behavior? How these reactions are very similar in terms of their behavior? Okay, so this is why when you run some acid-base reactions, you may observe some bubbles from these reactions. Any questions so far? Any questions so far? Okay, so let's keep going now. Let's continue our survey of chemical reactions. So in this case, we're going to look and we're going to try to predict the products from the following chemical reaction. And then our goal is to write a balanced chemical equation, total ionic equation, and a net ionic equation for each reaction. So I'll do the first example and then you'll tackle the second. So taking a look, what I'm first going to do is I'm going to dissociate all of my soluble ionic compounds, strong acids, and strong bases. So HCl is going to be dissociated into H plus and Cl minus. Okay, perfect. Do we dissociate aluminum sulfide? Do we dissociate aluminum sulfide? So HCl is a strong acid. What symbol does aluminum sulfide get? Is it soluble or insoluble? Aluminum sulfide. Is aluminum sulfide soluble or insoluble? I see a lot of students typing the solid symbol. That's exactly right. Aluminum sulfide is insoluble. Okay, so for our next step, if we want to predict acid-base reactions, what we are going to do is we are going to donate H plus to our basic atom. Okay, so we're going to write the product if we protonate our anion. So we have H plus. Oh, that's weird. Sorry about that. So we have H plus. Allow me one moment to reset OneNote. Give me 1 second. Sometimes it gets slightly overloaded when there are multiple files open for OneNote, and we've drawn a lot so far. Okay, here we go. So we're back to the problem that we were dealing with. So what we're going to do is we're going to protonate our anion. So we're going to draw the product if we fully protonate our sulfide anion. So we have H plus aqueous, S2 minus aqueous. And what we're going to do is we're going to cross our charges. We're going to cross our charges, and that in turn gives us a predicted product of hydrogen sulfide gas. Now, we're also going to combine and cross our aluminum and chloride. So we have Al3 plus, aqueous, and Cl minus. We're going to cross the charges, and we get aluminum chloride, AlCl3. Now, is aluminum chloride soluble or insoluble? Is aluminum chloride soluble or insoluble? So chloride salts are typically soluble, so aluminum chloride gets the aqueous symbol. So again, just in terms of the logic for predicting the products from these acid-base reactions, just like for your precipitation reactions, you swap your cation. In this case, you're swapping H plus and aluminum. You're going to write the formulas of your expected products. And fundamentally, in an acid-base reaction, you're donating H plus to your basic anionic species. Okay, so now that we have our predicted products in place, let's now write out our chemical equation. So we have HCl aqueous plus aluminum sulfide solid leads to H2S hydrogen sulfide gas and aluminum chloride. Okay, wonderful, wonderful. So we're almost there. We're almost there in terms of having a complete equation. Now, looking at this equation, just really carefully for a moment, is this equation balanced? Let's look. We have 1 chloride on the left, we have 3 sulfurs on the left, and we have 2 aluminums on the left. We have 2 hydrogens and 1 sulfur on the right. We have 1 aluminum and 3 chloride on the right. So, do we conclude this equation is balanced or unbalanced? Is this equation balanced? And don't be shy to type in the chat during this time. Is this equation balanced? No, it's not. Okay, so let's start balancing this equation. Let's start balancing this equation. So if we have 2 aluminums on the left and we have 1 aluminum on the right, 1 times what would give us 2 aluminums? What coefficient do we need? What coefficient do we need? 2. Yep, and as a consequence, we have 2 aluminums and 6 chlorides. Okay, so aluminum's balanced. Now we have 6 chlorides on the right, so 1 times what would give us 6 chlorides? What coefficient do we need in front of HCl? 6, exactly right. So now we have 6H plus to deal with. We have 6H plus on the left. 2 times what would give us 6H plus and 3 sulfurs? What coefficient do we need for hydrogen sulfide? 3, exactly right. Now, all we have to do, now that we have our balanced chemical equation, what we're going to do is we're going to dissociate all of our soluble ionic compounds, strong acids, and strong bases. Do I dissociate hydrochloric acid? Is hydrochloric acid a strong acid? Is hydrochloric acid a strong acid? Yes, so we dissociate it. So we have 6H plus, 6 chloride. Remember, our stoichiometric coefficient applies to all ions in our formula. We don't dissociate aluminum sulfide. Do we dissociate hydrogen sulfide? Is hydrogen sulfide a strong acid? Is hydrogen sulfide a strong acid or a weak acid? This is really critical. Do we dissociate hydrogen sulfide? And you'll notice by the way I'm naming this compound, I'm giving you a pretty big hint. Hydrogen sulfide or hydrosulfuric acid is a weak acid. So we do not dissociate it. This is why you need to be familiar with our table of strong acids and bases. Aluminum chloride, as it's soluble, we do break it up into its component ions. So 2 aluminum and 2 times 3, which is 6 chloride. Okay, now all we have to do is cancel our spectator ions. Do we have any spectator ions in this reaction? What are our spectator ions in this reaction? Yep, chloride. So then for our net equation, we have 6H plus aqueous plus aluminum sulfide, Al2S3 solid, leads to 3H2S aqueous plus 2 aluminum 3 plus aqueous. There we go. So this is a quote unquote acid-base like reaction. In this case, the base is the sulfide anion. Does this example make sense to everyone? Is everyone comfortable with the logic behind acid-base reactions? You handle them very similarly to precipitation reactions, except you cross your conjugate, you cross your basic anion with H plus to predict your conjugate acid product. Or more simply, as a general rule, swap your cations, write the formula, and from there, you're able then to balance the equation, cancel your spectator ions, and write out your net ionic equation. So, as we have reached the end of this first lecture period, we'll continue this lecture and we'll plan to lecture for around an hour in laboratory just to ensure we're caught up. So we'll take a quick 10-minute break. I'll see everyone at 2:33 in laboratory for our follow-up lecture. Can I get some confirmation that everyone understands what's going on at this time? Okay, perfect. So I'll see everyone in 10 minutes for lecture.